Greetings of the day. Good evening, everyone. Let's give the participants a couple of more minutes and then we'll start at 6:05. Let's wait for a few minutes. Okay, so greetings of the day. I welcome you all to yet another doubt clearing or problem solving session for the course Smart Grids Basics to Advanced Technologies, being taken by Professor N.P. Padhy and Professor Premlata Jena from IIT Roorkee. I am Swastik Sharma. I am a PMRF scholar at IIT Kanpur and I am a TA for this course. So last week we were discussing, we finished off what we were discussing in week 5 actually. We started with relays, how they work, overcurrent and directional relays. And we shifted our focus to newer, smarter microgrids. And we studied the operation and control of an AC microgrid. And we'll continue there from there and we'll build up to we'll discuss both operation of DC microgrid as well as operation of hybrid AC DC microgrid today. And yeah, let's start. So let me share my screen. Just a second. Okay. So, we will continue discussing about the operation of an AC microgrid. So, for a microgrid, there are four key control variables. So, we have voltage, we have just a second. We have voltage, we have frequency, active power, and reactive power. Now, we all know that for a reliable operation of power systems, for a power system to behave reliably and efficiently, there is a there is some limit set to both voltage and frequency, right? So so uh, these limits are generally, so let me say this voltage, it generally allows a 10% band, that is from zero point 0.9 to 1.1 pu. So we are allowed to move in between, not beyond that. Otherwise, it's called that our power quality has degraded. And for our frequency, according to IEGC, which is the Indian Electricity Grid Code 23, the band has been relaxed, and it has been relaxed from 49.9 to 50.05. So until and unless our frequencies and voltages are within these limits or within these bands, the system operation is said to be reliable. And we have two more components that we can control. One is the active power, and the other is reactive power. Now we all know from our previous power systems courses that the active power has a strong dependency on frequency, while the reactive power has a strong dependency on this magnitude of voltage. So varying Q, we can affect the change in voltage magnitude, and varying T, we can affect the change in frequency. And we all know how that change progresses, and we'll discuss it in the next slide. Now, why do we want control? So we can't let microgrids function as a standalone grid that we have established. So we need to know if a microgrid has converted from a grid connected mode to an islanded mode, and we then checked how to check that it has converted to an islanded mode, right? But now we are focusing on something which is a bit deeper concept, which is control over these microgrids. How can a central agent, how can a central entity, here this distribution network operator called DNO or distribution system operator, how can these entities affect or control our microgrids? Because at the end of the day, we want them to complement the function of our present day systems, right? But present power systems. So first, uh, so we all know the microgrids, they were established for uh, for for to provide power during this interruption of main services, right? So it's called uninterrupted power supply. So why this uninterrupted power supply is needed is, let's say there is a hospital, or let's say there is a school. So we need to be able to manage these microgrids, control these microgrids in such a way that they are able to provide an uninterrupted power supply to these critical loads, because we need these loads to function at all costs. Second, if we have a microgrid, we have a capability to black start. So what does black start mean? Let's say our system has gone into complete. So what happened in 2012? There was a complete blackout of the northern grid, right? So what does this black start do? They can energize small localized areas. Now, if these areas are localized, these can affect a change in such a way that we can power them in such a way that the whole region can be powered back. Because even for powering these generating stations, large generating stations, we still need power. And for these black start capabilities of this microgrid can be extremely helpful. Third, if we have a microgrid, let's say you are DGs, you produce excess of energy. So you would want to sell this energy to a market, right? To make profits. So uh, we can't just tell you to participate in markets. I mean, then there is a cost benefit analysis. You'll focus on profits, and the main output that was required, this uninterrupted supply, power frequency balancing, etc., ancillary services, these all will go down. So to maintain a balance, we need to control our microgrid. Now, in this microgrid, there are the control is categorized into a hierarchical control. So we have a global control. So this global control is issued via distribution system operator or distribution network operator. This system operator is given the responsibility to maintain the whole distribution system. So he acts as a centralized agent to to control the whole distribution network so that their functioning doesn't danger the power system's operation. So this global control is issued via DNO or DSO. Now, so what they do, so this distribution system is mostly a network of medium voltage and low voltage, right? So this medium voltage and low voltage network is given the responsibility to the DSO, and the high voltage is generally our transmission, which is given to the transmission system operator. Now, in each MG, we have three different levels of controls. One is the local control, the other is secondary control, and the third is central and emergency control. The central and emergency control is given to a microgrid central controller. So what it does is, just like a DSO has the power of maintaining the whole distribution system operations, this microgrid controller works in tandem. It works in tandem means it works with the DSO and takes in inputs from the DSO, takes in input from its own control algorithms, and focuses and issues control signals in a way to provide control over the whole microgrid. But uh, but we have local as well as secondary control as well. So we'll focus on what this local control does and how this local control produces effects in a generation or distribution of the loads. So generally, the local control is the lowest in the hierarchy, and it is a fast-acting control. It needs to be, right. So if let's say you have a system and it's plunging into a what say the control variables voltage and frequency are falling and it's plunging into a state of complete shutdown. So if your control algorithm is not fast enough, if your controllers are not fast enough, then what's the fun of having them in the first place, right? So being at the lowest of hierarchy, as the hierarchy goes down, the fastness of the controllers increases. So local control is fastest, then comes secondary control, and then comes central control. Will go to through each control one by one. So these are fast acting control, and these are mainly in the hardwares of the DG. So it's issued via the DG's hardware. So, so these controls affect the DGs to maintain a normal mode of operation. So this helps in controlling DGs for normal operation, right? So one type of local control is group control. So I guess I went through this the last week as well, what group control is, but we'll go through it once more. So what is group control? So what we have is our DGs work in a way that we with certain assumptions, we'll discuss what these assumptions are. With certain assumptions, we assume that our these DGs are mainly the power is dependent on frequency and the voltage is dependent on reactive power. So just a second, my screen is not. So what it does is we have a falling curve which is a which is a straight line with decreasing slope, and what it says is that it enables power sharing between two or more DGs. Let's say how. Let's say F naught is our normal operation frequency. So frequency for normal operation. We have this in such a way that it is the frequency of normal operation. Now, what happens generally is that this curve is used in such a way that an optimum power sharing is found out for both the generators. Let's say the group controls are something like this Gen 1 and Gen 2 curve. For F naught frequencies, we have two different kinds of two power levels for generator 1 and generator 2, given by P1 naught and P2 naught. Now, let's say under certain disturbance, the frequency fell. If the frequency fell, so if the frequency fell, our generators changed their so our generators will have to change their output, and this change in output is given by these two differences. So they made for a delta F change, the P1 goes through a delta P1 change, and the P2 goes through a delta P2 change, and is at a new P1 and P2 this P1 and P2 points. Now, if we want to go back to this curve, if we want to follow in such a way that we want to bring our curves back to our normalized uh, frequency, these power levels are then again arranged based on how much the disturbance was caused, delta P1 and delta F, which is calculated using this. Delta F is nothing but minus Kp and delta P. This minus Kp is your droop coefficient. So based on this group coefficient, you find out the optimal arrangement, the optimal power sharing between the two generators to work at a new frequency level. And similarly, for QV control as well, we have similar kind of a story. And here the relation is given by minus KQ delta Q, and KQ is your droop coefficient. Now, since the slope is falling and it's a decreasing slope, this negative sign comes into picture. Now, so do you know what the assumptions were when we formulated for this loop control? So you must have gone through that Newton-Raphson load flow and fast decoupled load flow, right? There we came up. Can you say basics of group control? Was it, what is its use? Okay. So let's say you have this is your profile and this is your group level, right? So let's say this was your optimum function and this is P naught F naught, right? Now what happens is usually whenever your frequency tumbles or it changes its pattern, your power level needs to be changed. Let's say your frequency went into a new location, which was this F, and it was beyond your permissible level. So F is greater than, let's say, 50.5 hertz, or let's say 50 hertz. And for normal operation, you want your frequency to be at 50 hertz, irrespective of what the issue was. So what you do is, uh, now you have this new operating region, right? This is your P1. So to work at this, this is the amount of power reduction, or this is the power reduction that would be caused if your frequency goes to a new level. So what you do is you shift this droop curve. You have droop controllers to fix this droop curve in a way that what happens is your new frequency would match completely with the uh, F naught one. So it shouldn't be, since it increased, I have to decrease this. So you produce. Hmm. So now you know you need to decrease your power level by delta P amount to be able to reach back to your F naught frequency. So what you do is you shift your droop curve. Once you shift it, you can see that at P1 level, your frequency will now match exactly at F naught. So this droop control, what it does, it shifts this curve up or down based on how if your frequency has decreased or increased, and then it matches your P1, which was going to be which is your new equilibrium point, to be able to maintain the frequency that was there originally, which is your normal basics of basis normal operation. So This droop control, you shift your curve in a way to match your normal operating frequency at all times. So that is the way how your droop control works. It produces a change in your coefficient. This is it dependent on frequency. So what is dependent on frequency? Can you tell me it? What does it signify? So we are talking about P and F, right? P is dependent on frequency, and this delta F is nothing but your droop coefficient minus delta P. So you're changing this droop coefficient to change your curve. So that's what you're doing, right? Is it dependent on frequency? I don't understand what it means. Can you elaborate, Kshitij? You can unmute yourself. Thank you, sir. But how it's shift based on KP values? Basically, what will happen if in generator's case and in inverter's case of RE? So, so there are algorithms that are used. So in your generators, your synchronous generators, you have these automatic governor controls. So these control your these are commands issued from your NLDC, your National Load Dispatch Center, which which help the generator in achieving the new equilibrium point. In inverters, we use control algorithms that we will discuss ahead. So I don't know if sir hasn't taught these control algorithms for inverters, but there are these inverter control algorithms where you constantly change your impedance in such a way. We'll talk about what this KP is basically. Let me complete this first, and then we'll talk about what this KP is, and then you will be able to know how, in case of RE, we can effect a change in this KP. But Kshitij, I am unable to tell if so. These are not parallel, so these can be like this as well. So you don't have to think that I'm just taking parallel. It's just that it was easy making it parallel. Yeah, Kshitij, what is dependent on frequency? I don't understand your question. Okay, so that's how they do. So, but generally, what we do is we have multiple generators working in parallel, right? So, what we do is we add one more generator, or we change it in such a way we change the KP values in such a way that both the generators match in a way to operate at a normalized frequency of operation. And this is all dealt in. This is called this whole thing is called automatic load frequency control (ALFC), where these commands of changing KP values are issued through an AGC, which is a governor control, which controls how much power is being input uh, to the generator at any given point of time. So where was I? I was discussing something. So I hope I was able to answer your question. I don't know what your name is. You have written just dot. So we'll talk more. Yeah. So we'll talk more on how KP values are. Yeah. Yeah. Who is saying? Okay, so we'll talk more on what these KP values are and how for inverter we implement this loop control. Okay, so where was I? Yeah, but yeah, I was telling you something. So this strong dependency, can you tell me from your experience with load flow, if you have studied load flow, how this strong dependency came into play of P and F and Q and V? So this decoupling, why do we do this decoupling? How does this decoupling come into be? Anyone? Okay, what do we assume our load to be? Or what do we assume our impedances to be? Okay, so this strong coupling between frequency and power in Q and V are a product of uh, low R by X ratio. So we assume that mostly our impedances are inductive, which is we have a high inductive impedance, and Due to this high inductive impedance, the dependency of Q over V and P over F comes into play. So to know more about this, I would ask you to please go through fast decoupled load flow, and there you would be able to understand how this decoupling comes into effect. Now, because we assume that our R by X ratio is low, which is true for transmission side. Now, microgrids are mainly enabled at distribution side. For distributions, this assumption low R by X ratio doesn't hold true anymore. So the R by X ratio becomes higher. Now, with high R by X ratio, we can't assume our impedance to be purely reactive. We have a resistive component to it as well. So our power will be dependent on both frequency and voltage, and similarly for Q. Now, this inefficiency due to the assumption causes uh, causes the power sharing to be different for the analyzed case from the real world case. So what we can do is we can use these new control methods, which is called a virtual impedance method, an adaptive control, a droop control method, angle droop control method, virtual frame transformation, and virtual inertia based droop control. Now, just a second.
Hello.
Yeah,
So while you are comparing with this average ratio and P and Q,
Tesla and
is
Elon.
there any R-base ratio and P directly proportional to F, Q directly proportional to V?
So your voice is very, it's like it's echoing too much. Can you write? I'm unable to guess your words.
Yeah, yeah.
Yeah, I'll wait for you to write. How R by X ratio is related to PQ? Okay, so I gave you gave this to you as an assignment, but let me tell you. So what happens is usually, um, so I have to go through whole power flow analysis, but I'll try and sum it up for you. So when we write the expression for apparent power, it's Sij for power flowing between buses I and J. What we have is we write it something like this, right? Now, what usually happens is these will have, if we assume, let's assume that our our this let's derive. So what happens is mod of Vj, we have, I shouldn't like this, it was simply Yij. This was just a second. Vi, Vj, Yij star, because we write it as Vi star, right? So what happens is this becomes Vj, this will also become Vi Vj, and we have some, let's say, R component, Rij minus J Xij, and angle delta I, and this will have Vj angle delta minus delta J because of that conjugate, right? Now, let's assume our R by X ratio is low. So if this is the case, we can assume that R is very, very less than X. So we can remove R from the this term. Let me add one more page. So what will this become? This will become Vi Vj angle of delta I minus delta J, and this will be minus J Xij. Mm, Xij and angle. So minus delta I is nothing but minus j is what? How can I write minus j in polar coordinates?
minus 90 degree.
Yes. So it will be minus 90 degree. So your term will look something like this: Vi, Vj, Xij, angle of delta I minus delta j minus 90 degree. Now this is your Sij. Now let's try and find out for Pij plus Qij, because Sij is nothing but your Pij and Qij. And this would be your cos of delta I minus delta j minus 90 degrees plus j times sine of delta I minus delta j minus 90 degrees. Right? So Pij is what? Vi, Vj, Xij cos of delta I minus delta j minus 90 degrees. And Qij is what? Vij, Xij sine of delta I minus delta j minus 90 degrees. Now, just a second. So I got you two terms. Now, can you tell me, let's say our delta I minus delta j, sorry, can you write this term can you remove 90 degrees from it? So cos of a minus 90 is what? A. So when I did this dot, whatever your name is, so when I did this, just remember I included this assumption r by x is very, very less than, so r is very, very less than x. This assumption I've taken. This you agree, right? So now, so if I write this, I can write this as something like what of vi, vj. Yeah, what will this term be? Cos a cos b plus sin a sin b. So only what term will remain? Sin b, right? So this would be sine of delta I minus delta j, and Qij will become Vi, Vj, Xij. And what will this term be? Anyone? What will this term be?
C
Sa-
cos of delta
Okay, just a second. Your voice is breaking. I'll do it. Sin A minus B, right? So sin A cos B minus cos A sin B. So it would be cos of delta I minus delta j. Now I got you two terms. So hmm, now let's do small angle approximation. So delta I minus delta j is generally treated to be very, very small. It is close to zero, not zero exactly, tending to zero. So what we do is we write sine of delta I minus delta j as delta I minus delta j, and cos of delta I minus delta j becomes 1. So what is your Pij? Pij is nothing but mod of Vi, mod of Vj, Xij, delta I minus delta j. So my handwriting is a bit weird. If you are finding it trouble reading, just let me know. I'll do it once more. So minus Vi, Vj, Xij. Now, in the in both of these terms, there is a peculiarity. In one term, you have angle difference coming into play. So this angle difference is what, so generally we treat delta P to be dependent to this delta delta, that is the phase angle difference. But this phase angle difference, if you know how this works, so the phase angle difference produced at the synchronous machine side is what contributes to the frequency, because delta omega is what? Delta delta by delta t. So we generally take this assumption that if this is the case, delta p then will be dependent on delta f only. And here you can see that delta q is what? Dependent strictly upon the the voltage magnitude. So we started from this assumption that there is a low R by X ratio. That's how we decreased and we started decreasing to come to the fact that active power will affect the change in your angle, which is then dependent on your frequency. If this delta omega by delta delta upon delta d holds true, and the Qij is dependent on your voltage magnitude. So that's sine zero is zero. No, sine zero is zero, but I'm not saying it's completely zero. It's close to zero. And if you do small angle approximation, sine of a very small angle is equated by its small angle only. Because since it's small, it won't change much, right? And cos of delta I minus delta j, since it's cos of close to zero will also be one. So that's why we include one only over there. If you do small angle approximation, you will know where yeah. So that's how this whole dependency on frequency and voltage magnitude comes into play. I wanted to give you this as an assignment, but since you asked, I talked about it. So now where was I? I forgot. Yeah. Um, what was I discussing? Yeah. So let's move ahead. So yeah, where was I? I forgot. So yes. So this inefficiency that happens because of R by X ratio not being very small. This causes the power to not be completely dependent upon frequency, but also on the voltage magnitude as well. So what we do is we introduce several new methods to advance our local control method, which is the loop control method. So in the first, we is called virtual impedance method. What we do is so dot. Did you understand the complete picture, or shall I repeat anything else so that just give me a thumbs up if you want me to move ahead? Got it. Okay. So in virtual impedance method, what we do is, since we can't really change the impedance of the line, what we do is we insert another impedance. So what we do is we insert an inductor between converters and AC bus. So where the converter is connected and where the AC bus is connected, we introduce an inductor. This inductor, what it does is it causes the impedance to look as if the R by X ratio is very low, and hence a better droop control could be a better droop control could be done on the inverter side of the system. This is the use of virtual impedance. So we insert inductor between converter and AC bus. Second is adaptive droop control method. So in this droop control method, what we do is, so basically this Kp value is nothing but it's a measure of your impedance, if you look at it in a way, because you are creating an effect on the impedance to be able to better manage your droop control. Now, if you can somehow dynamically track this Kp value, this impedance, based on how your real-time grid conditions look like, microgrid conditions look like, you can exert a control over you can exert a local control. So what you do is you dynamically adjust this. So this is one way where you can increase the efficiency of your droop control method. Second is the angle control method. Now, if you remember, I told you power is dependent on your phase angle difference, right? But what we do is we equate delta omega in such a way we call, okay, if delta by delta t is equivalent to the angular frequency of your this synchronous generator. So let P be dependent upon frequency as well. But if you use this angle droop control by constantly taking into account the phase angle difference between AC bus and your voltage source converter, you can affect a droop control. And this droop control is better than PF control because you are not taking that assumption into account. But here you would require communication infrastructure to be put in that converter side as well as your power line side, which is a costly affair. Another thing you can do is, since you have three-phase AC quantities, you have three-phase AC quantities. What you can do is you can convert these AC quantities to a different domain, a different transformation to a different axis. So one axis is DQ axis. So this is called Parkes transformation. And in this Parkes transformation, what you do is the D axis quantity is used for power control, active power control, and your Q axis quantity is used for your reactive power control. And using this virtual frame transformation, you can affect a change in your system. And the other thing is virtual inertia based loop control. So what does virtual inertia do? So it is used to add another layer of so what is inertia, if I ask you? So whenever a rotating mass rotates, if you tend to take away its rotating power that is causing it to rotate, let's say there is a turbine, it's rotating. How is it rotating? You are making a stream of steam fall into it a certain point that it helps the turbine to rotate. If you remove this steam, what would happen? It will continue its rotation for a certain amount of time. This is called inertia, because once the power that is causing the effect in the system is removed, still it tends to stay in that position. This is the inertia of the system. But in renewable energy sources, you don't have inertia, because there are no rotating parts involved, right? So what kind of inertia you could have? So what you can do is you can introduce a virtual inertia. Let's say you have a PV panel, and instead of operating at the maximum power point, what you do is you operate at an off MPPT point. It can be anything, 10%, 10, 20%, 15%, anything, so that you have a headroom. And in this headroom, you can increase or decrease in a certain way to control the output, so that the control of active power could provide control in the frequency. So this is in a way you can exert control over your um, um this uh, this can be used for to control your group characteristics. Now there is secondary control as well. So this secondary control, what it does is, I have to write it. So I talked about secondary control, right? So this is next in line of the hierarchy. So what it does is it helps in monitoring the local control. If let's say your local control doesn't produce the desired amount of effect, you have a control to bank on. So in case you just a second, sorry. So what you do is you use this secondary control to produce an effect once your. So what it does is it produces an effect if your local control doesn't work. So that's the use of your. So that's the use of secondary control, and it is a bit slower than your local control because it is used after the local control doesn't issue a control signal. Then the secondary control comes into play. Then you have a central control. As I said, this is the control that handles the whole microgrid operations. So local control, its usage was for a particular set of hardware. Then came secondary control to assist the local control. Now you have a central control that issues control signals for the whole microgrid, to control the whole microgrid. So its main function is supervision of your microgrid, right? So all the microgrid activities, be it to participate in a market, or to do islanded mode of operation, standalone operation, grid connected mode. All of this is done by your this central control. It's also called microgrid central control as well, but it's central control. And then you have one more task that it's responsible. It's responsible for energy management. So what is energy management? So it's a set of control tasks. Let's say one thing doesn't happen. So you should have a whole chart, a whole strategy in place to be able to effectively manage your resources. So let's say you have a battery, it is connected to a PV. Now you should have a certain threshold that the battery should come to before being able to work in off MPPT mode, or it should be at a certain charge level to work at the MVP mode, etc., etc. So this is the energy management scheme that helps in performance of your microgrid. Third is it can detect and issue commands for islanded and grid connection mode. Or if my handwriting is poor. And one more thing it does is it works in close relation with your DSO. Right. So this is what the whole thing was, and then I talked about global control, and its use is to manage the power flow between your microgrid and your distribution system. So now these all things, this whole P, Q, V, and F, these are applicable only to AC microgrids because that's where frequency component is there, right? So what if you have a DC microgrid? In a DC microgrid, there is no frequency, right? So how will you control your microgrid? So the control variables decrease. Instead of having four, you have only two. It's active power and your voltage. So how will you produce an effect in your DC microgrid? We'll discuss. Okay, so we'll discuss operation and control of your DC microgrid. So what does DC microgrid do? So as I told you, there is an absence of frequency. So if frequency is absent, there is no PF control. And if there is no PF control, how will you control your microgrid? So the control that you want is control over your voltage, your bus voltage, your DC link bus voltage. So in this DC link bus voltage, you have different types of control schemes. One is a decentralized control, the other is distributed control, and the third is the centralized control. So we'll discuss one by one everything. So in decentralized control, what happens is all of your forces, all of your loads and your forces are controlled independently. So without supervision, your all of the sources are controlled independently of whatever the so there is no one person asking you to control your equipment. It's just your hardware that is controlling all of your sources. So this is called decentralized control, giving the control uh, to the hardware itself. Then comes distributed control. So before going to distributed control, let's discuss centralized control because that's how distributed control comes into play. It's a mixture of both decentralized and centralized control. So centralized control, what it does is all the controls of the source is done from a single point. That's what was happening in the previous control algorithms that we were discussing. So all the control happens from a single node. So for this, your but what happens is if only one person issues your command, it won't be able to look after a whole bunch of loads. Let's say you have a very wide network. So you said is low, then only the direct. What are we? That's what I discussed. Now, if we can't neglect R, what will happen is your power will be dependent on both voltage as well as frequency. So if there is no there can't be a group control, right? Because your power is now being dependent on two different quantities. So changing one will produce change in two quantities. Earlier there was only one change. Power was changing, frequency changed. Frequency changed, power changed. If sorry, active power changed. Now, if voltage changed, your reactive power changed, or reactive power changed, your voltage changed. But now both of these quantities are dependent on both of these frequency and voltages. So how will you produce an effect? So your normal droop control, your conventional droop control is not uh, applicable anymore. What? So that's why I discussed now. We introduce virtual impedance. We add an inductor so that the whole R by X ratio theory could come into play, and your system, your impedance system's impedance assumes to be inductive in nature, and that's how your loop control could then be used. Did you get it? Yeah. Okay. So where was it? Yeah. So all the control happens from a single node, right? So it has to look over a wide area of network, and that's difficult. So what happens is your reliability reduces. In decentralized control, since all the components were behaving independently based on a few references, let's say some references were given, and the control algorithms were issued differently decentralized, right? So the reliability was there, and but in centralized, reliability decreases. In distributed, to maintain reliability and to make sure there is a central work function that's causing control in devices. So what it does is, here control functions are distributed throughout the network. So you could have multiple central operators. So in this way, we can maintain reliability, and we can maintain uh, what way was I? Yeah, we can maintain reliability. Now, let's talk about decentralized control. So in decentralized control, let's say if it's kind of like your local control, right? All of your device hardwares are behaving independently. So there are four different kinds of these decentralized control. One is your loop control, then voltage leveling, DC bus signaling, and power line signaling method. Right. Now, as I told you that TF won't be valid anymore. So how would you do it? So if you see, your power is what? In a DC circuit, your power is directly proportional to the current in your that is in your circuit, right? So power is directly proportional to current. This is one component you can issue, right? So what you see is the output, the current output of your converter. How does it look like? It looks something like this. So if let's say you have an nth converter, VDC n represents the DC voltage of your nth converter, and there is some reference VD star given to it. So the whole equation looks something like this. The output current of that nth converter multiplied by the resistance of that output resistance of that nth converter, right? Now, if you look at it, now you can also see that delta, let's say this is called delta V, and I is what? RDCN. And this is a constant value. This won't change. Impedance is constant, right? Now, as you can see, changing delta V produces an effect in your I, your current. And your current is what? Power. Power can be written as I square R, right? So whatever the value of I be, your power is directly, your relation between power can directly be found out. So, so what you see is here, changing V, you can produce a change in your current. So if you can see here, assume these two curves. Similar loop control characteristics could be developed for your DC side as well, which is what? V versus P, or V versus I, right? But but these loop control these loop control characteristics are not your ordinary characteristics. These vary, the deviations vary very widely. Like in case of your droop control for your normal synchronous generators or your inverter based AC based microgrids, what happened was that droop control quantity was very less. The coefficient was used to be a lesser quantity. It didn't vary very much. But here the variation can be very much. We can have a very small droop, and we can have a large droop as well. Now, due to this small and large droop, what happens is your voltage deviation and your current deviation is also different. For a small droop, if you can see, the voltage deviation is very small. but your current deviation is too much, right? And for a large group, what happens is your voltage, sorry, here, your current deviation is, even though it's less, just a second. Yeah, for a large group, your current deviation and your voltage deviations are less, but for a small group, opposite happens. So to control this, so to control this, your control algorithms need to be effectively changed and managed. And for this, we introduced some novel concepts of adaptive group control and virtual resistance based group control. Similar things that we did in AC, but we are implementing for DC side as well, keeping in mind that there is no frequency component now. So the first group control was virtual resistance based group control. So what we do is we take we usually neglect the line resistance. So line resistance uh, wasn't taken into account before, but here we take into account lines resistance as well, and this line resistance can be changed based on whatever we want to add to it, right? Earlier, we were doing, we were adding an inductor so that our line behaves as a low R by X ratio line. Here, we can change the resistance of the line. Once we take the line resistance into account, the equation would look something like this, which is some reference voltage plus the earlier compensator voltage minus your nu. So this delta V naught, it's just a second. Yeah, yeah. So your delta V naught is, let's say you have a certain, it's a compensation for your secondary and your group control method. So generally it's taken. So since the paper had this delta V naught into play, I added it. Even if you remove, it's just a constant quantity. You can just treat it as a constant quantity. And as you can see, your new resistance value is also dependent on your how your voltage changes with respect to your output current, and you can in a way affect the change in your group values. Second way is to do adaptive group control. So what we do is we employ group control based on based on change. We adapt based on how our RV group changes. So this RV group is constantly or dynamically um, uh, monitored based on how the grid conditions look like, and we change the group control whenever the change is produced. So what it does is, by using this, we can minimize how the current sharing difference between both the between different converters of the DGs is used. And also there is a concept of circulating current. So in a DC circuit, there is a concept of circulating current. So you must have seen Sir mention this. He didn't explain it, but let me give you a brief overview of what is circulating current. Managing RV could help produce an effect in this circulating current as well. So what circulating current is? So in DC microgrids, which have DRs that have DC output, let's say solar panels. So what they do is they are connected using a DC to DC DC to DC converters. Now these DC to DC converters, what they do is they regulate voltage and current flow. If the voltage is changed, if your voltage is changed, your current will also change. And in a way, you can monitor and regulate the DC bus voltage as well using the DC to DC converter. Now let's say the line connecting these converters, these DERs to the DC bus, they have different impedances. If they have different impedances, what would happen is all of this voltage drop that is happening in this different in this resistances of different lines, these won't be equal. So if they are not equal, the current flow from different DERs will vary because the impedances are different. Even if you're changing your RV based on how your DR responds, the line connecting to the DC bus are different. These are natural, right? You can have different manufacturing defects or something like that. So if this happens, your voltage drop will be unequal in different sides. If these voltage drops are unequal, the currents will start flowing from a high voltage side to a low voltage side. Let's say in a different converter, this voltage drop was less. In a converter, the voltage drop was more. So since the voltage drop in this converter is more, it will have a lesser voltage. Since it has lesser voltage, the voltage from this side where the voltage drop was less will make power flow to this converter. So what happens is this causes a circulating current flow between different DER due to mismatch of voltages. Using RV droop, using this line resistance by taking into account line resistance, we can manage to minimize the circulating current as well. So these are in a way, some way we can control the uh, droop of our lines. Sorry, systems. Then we have intelligent technique based droop controls. We can have fuzzy logic. So I would request, can you please repeat? Okay. I I am basically a very slow. It's because it's already 7 and I haven't covered half of this lecture. Anyways, so what happens is, let's say you have this line, right? This is a DC bus. So you have a DC to DC converter connected to, let's say, a solar PV, and you have a DC to DC, let's say, sorry, let's say to fuel cell. And I think it's very bad to the fuel cell. Right. Now what I'm saying is, let's say the impedance, this, sorry, this resistance R1 and this resistance R2 is different. If this resistance is different, the voltage drop that is happening, this IR voltage drop, IR1, sorry, I1 R1 and I2 R2, these voltage drops will also be different. But what we say is these bus voltage should be at one voltage level, right? Let's say there is a mismatch of this voltage. Now what will happen? Let's say this V1 is greater than V2. If this is the case, what will happen is a current will flow from a high voltage to a low voltage path. A current flows from high voltage to low voltage. This you all know, right? So this will cause a current flow from this side to this side. This current IC will call. This current is called a circulating current. Now what I'm saying is controlling RV droop that I mentioned here. This, sorry, it's not called RV. Let's say it's this RV. We can control the droop or the resistance of these lines, right? Because in a way we are producing change, this R, we are introducing an additional resistance into our circuit. So this resistance, what it does is this causes to minimize this current flow. Let's say this, since this I2 R2 is greater than I1 R1, what we do is we insert a resistance in this R dash. If these two match, these will also match. Since both the voltage drops are matching, the current, circulating current will not be there anymore. So controlling this, adaptively controlling this droop will cause our resistance, this circulating current to be minimized. So did you get it? Yeah. So okay. So mode adaptive droop control. So what this mode adaptive droop control does is, so we have two types of mode. We can vary in such a way that we can enter either a droop control mode or a constant power mode. So in droop control mode, we change the power to produce change in voltages, while in constant power mode, we inject the same amount of power. So I won't go into detail between these two. So I hope you have went through that lecture. Sir has explained in deep about these two. Now coming to distributed control. So what does distributed control do? It is it if there we distribute control functions throughout the whole network. So the first one is digital average current sharing. So in this, what we do is to manage the voltage and load sharing, we check the the current the output current of all the sources, and we create a signal that is able to detect which the share whose share in that current is more. So this share comes through this value ik, so average. So we average all of the current from all the different dr. This is IGPU divided by n. Let's say there are n drs, so we average all the current from all of these drs. Now we change our conventional droop control characteristics. So droop control is what? Dependent on R, V, um, I naught, right? So what we do is we change it, we multiply this IK average and we multiply our I naught with it. So what it does is, based on how much what the output of the whole system is, we average the current and we issue control signals in a way that matches the output of all of the sources, so that all of them can produce control whenever they are required. So in this way we modify our original conventional loop control by multiplying IK average with it. This is one. Second is average voltage sharing. So we can do the same thing with voltage sharing as well. So what we do is, from a pilot bus, so I won't explain it deeply. So from a pilot bus, we check what the reference bus voltage is, and then we distribute the volt. Similar to this, we just do the same thing, and then we distribute in a way to produce the RV drop based on what the average voltage contribution from each resources is. Next is distributed cooperative control. Now, this is something that I want to talk about in depth. So what it does is, these two are same, and this is something new. So this works on the theory of multi-agent systems. Now, in a multi-agent systems, there are multiple different agents. So agents are what? Actors, let's say. Multiple actors that work to attain a common objective. But all of them work independently. Let's say, let me give you an example. So, okay. So let's say IAS, right? So there are different administrative services, right? All of them are recruited at, let's say, deputy collector. So all of these deputy collectors are posted at separate locations, different locations, right? But all of their common goal is what? To achieve some task that, let's say, prosperity of the nation. So all of them work independently, work it on their own areas to achieve a common task of prosperity of the nation. Similarly, in this, there are multiple actors working to attain a common objective. That is why it's called a cooperative control. There is one more control, it's called competitive control, where all of these actors fight among themselves so that to achieve an objective, which is a competition based objective. So let's say you have that, what was that game? Squid Games, right? Squid Games. There are multiple people and they were competing against themselves to become what? The topper of the whole game so that they can get money, whatever the money was, I forgot. So this is how the multi-agent systems behave. So there are multiple actors. They all work in an environment to achieve a common goal. Now in this, what they do is we have different storage devices, right? So in this, the actors are storage devices. These can be your batteries, your ultra capacitors, super capacitors, etc. And their SOC are controlled. Their SOC are controlled to achieve what? To achieve that, at any given point of time, no energy source should have a deficit of energy. If so, based on this, we can control the battery resources to control P, which can then use to make effect on the voltage as well. Now, For microgrids, there are two kinds of operations we all know. One is the grid connected mode of operation. The other is the islanded mode of operation. We all know what grid connected mode of operation is, and we all know what islanded mode of operation is. So I won't go through the definitions of both. We'll just continue. So in islanded mode of operation, there are two different kinds of operation. One is a single DC microgrid operation, and the other is multi-islanded DC modes of operation. So let's discuss one by one. So in single islanded mode of operation, what happens is this the this control, as we discussed, could be of centralized, decentralized, or distributed, right? So what we do is this so yeah, where was I? Okay, so this is what, so in here what it is, there's just a single microgrid which works on its own to be able to fend for itself. So in islanded mode of operation, what it does is the generation, localized generation should match the local load. It has to serve only its local load. And this load can be of different types. Let's discuss. So we have a single microgrid, DC microgrid, which is islanded, let's say. We have PV panels, we have a hybrid storage system, we have a PMSG wind, we have some loads, and we have a grid side converter. So what it does is this grid side converter is connected to the utility grid. Let's say for an islanded mode of operation, this utility grid is no more there. So all the loads have to be met using the localized generation only. Now what happens is usually if there is a battery storage present in such an islanded DC microgrid, so what we do is we use it to control um, the microgrid. Why? Why do we use battery storage to control the microgrid? Can anyone tell me? We have different generations. We have distributed renewable resources, but why we are using battery storage to control the microgrid? Anyone? No one? Okay. So we use battery because yes. So we, because the output of the renewable is not in our control. Whatever we are getting based on what the conditions are. We can't control the climate conditions. So if we can't do that, yes, you are right. If we can't control that, we need an efficient system that is there when it's needed for control over that. So we use batteries to affect the islanded control. But in multi-islanded DC microgrids, there are multiple microgrids. So what we do is we form clusters. So let's say there is MG1, MG2, some MG3. So a cluster is formed where all of these microgrids will exchange energy based on how much deficit or extra they produce. Let's say MG1 produces less and MG2 produces more. MG2 can then pump power to the MG1. But individually, they are also controlled using your battery only. Because battery is the one thing that can regulate your grids because we don't have precise control using the other renewable generation. So let's talk about a single DC microgrid once more. Let so we have, I discussed, we have PV panels, we have hybrid storage system, we have a wind system, we have loads, and we have a grid side converter. So we know PMSG wind, what it is we have a, I already discussed in week 2 or week 3. So this wind system is consists of a turbine and a generator, which is generally an alternator. This produces power in AC mode, and then this AC mode is converted to DC, which is then boosted using a DC-DC converter and then connected to a DC bus. So because it's a DC microgrid, the main bus should be DC. So that's how a PMSG works. Then there are loads. Loads are of two types. One is critical load and the other is non-critical load. Let's say your generation, when it's working in islanded mode, your generation is not sufficient to meet all the loads. So what you do is you prioritize your loads. So you check, oh, we have schools, we have hospitals. So first, these loads should be powered. Then the residential loads can be powered if the power is there. If there is no power, these residential loads are then left out because the priority is given to your hospitals and your schools because these are critical loads. Then we have a hybrid storage system. So as you can see, we are using a hybrid storage system which consists of two storage elements. One is a battery and the other is ultra capacitor. One is ultra capacitor. So what it does is, so usually your battery, it has high energy density but low power density. So high energy density means that it can store a large amount of energy, but when it comes to supplying power, the amount of power that it can use to supply the amount of power that it can supply is limited, is very low. But ultra capacitors have low energy, that is, they don't have a large storage, but their power density is high. So now you must be thinking, why use storage like this, right? Let's say there are frequent switching operations happening. You have loads which are switching on and off. You have different generators which are switching on and off. So if your battery is used to meet these frequent changes, what it does is it will spend large and then it will charge again. So this whole thing will cause the battery to wear out much faster because it's not meant to be used like that. But if you use an ultra capacitor, these fast switching transients can be met through these ultra capacitors, and your battery can then use its normal power density to reach the desired characteristic or operation. So this safeguards our battery from a wear and tear, a large wear and tear. Then you have PV panels. These PV panels produce DC output, and these are used in MPPT until the battery is charged. So why we are using it at MPPT? So you extract maximum power from it, use some of that power to charge your battery, and rest of the power to be given to the grid. But let's say your battery is charged. What you do is you can't charge it after that, right? So what you do is you shift it to an off MPPT. So let's say because you want to regulate the DC voltage, you can't just inject power just like that. You need to regulate the voltage as well. And for that, it shifts between off MPPT and on MPPT based on that. So this is how a single DC microgrid operates. So any doubts up until now? We'll move ahead then. A thumbs up or a thumbs down. Okay, and there's no, yeah, clear. Okay, so as I said, there are two kinds of mode of operation. One is a grid connected mode of operation. The other is an islanded mode of operation. So in grid connected mode of operation, you take extra energy, which is this energy from your, this power from your AC grid or your utility grid. This power is what? After meeting your load from your localized generation, which comprises of what? Your wind, PV, battery, ultra capacitor. You use it, PV, I should write. You use it to meet your load, and the rest of it you take from your utility grid. But in islanded mode of operation, your battery is what is used to power all of these loads. So this acts as a reference in your islanded mode of operation. Earlier, it was PGM that was acting as your mode of reference. So this is wind, PV, and your ultra capacitor. So, yeah. So what happens is usually you can't supply all of your load. As I told you, load shedding is pertinent because all of your battery cannot be used cannot be used to empower all of your loads. Let's say your generation from your renewables is low, but your loads are high. You can't meet that. You can't use all of your battery to meet that load because battery has to regulate voltage as well. So what you do is you shed some of that load by categorizing them into critical and non-critical loads. And opposite happens during conditions when the generation is high and you have light loading. Now let's move on to another type of grid. So I went through AC grids which have AC main bus, and we went to DC grids which had DC main bus. But what's the difference? So we are using converters, right? We used converters to change in such a way to match the AC side and DC side. What if we can have both? We can club them into a hybrid microgrid by having one AC bus and one DC bus. we can then have different sets of loads, AC sides and DC side, to power this. And this is useful also, because then you will utilize both your renewables and your uh, synchronous generators. So this can help you in do three things. One is your AC and DC bus can both be connected, interlinked as well, and then they can serve to each other. And two, you can achieve a robust coordination between your AC and DC subsystems. Third, your structure is considered, such structure is considered when major power sources include both AC and DC. Let's say you are at a place, you have synchronous generations in form of wind available and your PV panels also. So you can have a hybrid microgrid. But it's a booming topic. I mean, it hasn't reached its full potential. There is still research happening in it. And we'll today discuss some of the control strategies and power management schemes for this. So, as you can see from this, this is one structure of an AC DC hybrid microgrid. As you can see, we have DC distribution generator, AC distribution generator, and storage elements at the DC side as well, which are converted using DC-DC and AC-DC converters and bidirectional converters and connected to a DC bus. We have an AC side as well, where we have AC distributed generation, we have DC distributed generation, and we have storage elements, and we use converters to connect to the AC bus as well. And we have loads, localized loads, and we are also connected to the utility grid from the AC bus, because your AC bus, you don't require a converter to connect your AC bus to that. But it contains both kind of resources, right? So what's the fun of having this? I mean, you still require converters, and controlling converters is a tough task, because your converters are your costly affair. These power electronic equipments are costly. So what you can do is you can have a simple structure where you can have an AC side and a DC side, where you have only DC sources and loads for your DC microgrid, and only AC source or loads for your AC microgrid. But yes, both kinds of structure are possible in an AC-DC hybrid microgrid, because it's your, you can connect however you want, right? Uh, so this is how it's achieved. And uh, uh, now we'll discuss the control strategies and power management schemes for this. So, mm, so we discussed for a DC side separately and AC side separately, right? Now you would be thinking we can use both of them, right, individually, and we can then control this AC-DC hybrid microgrid as well. But that's not how it works. We have different schemes, because because we have two different kinds of buses now, and these are also connected to each other using an interlinking converter to exchange power. So we need to have a particular uh, um, control such that we are able to meet all of our objectives. So we'll see, this is a challenge. It's not possible as of now. That's why we use power management schemes to be better able to manage these resources. Let's talk about that. So, yeah. So control strategies are still being developed. Their operation and their control is very difficult. We'll discuss in the challenges. I'll first discuss what is power management scheme, PMS. So PMS is nothing but it determines what your output active power, your output reactive power of DGs, storages, and control V and F at the same time. So we control PQ from individual DGs and storage elements to affect V and F as well. But now you tell me, for a hybrid microgrid, can you have a global variable where you can track? So for AC DC microgrid, you had four different global variables, right? Your voltage, frequency, power, and reactive power. For DC microgrid, there were only two: active power and your voltage. But now here you have two different kinds of grids. Can you have one global variable? So in an AC microgrid, your power, we developed a way where your power can be used to affect a change in frequency. But in DC microgrid, that power will affect a change in your voltage. So we don't have a global variable in the DC microgrid. So due to the absence of global variable, controlling AC-DC microgrid is difficult. It's a difficult affair. So due to this, your conventional Drup algorithm is not applicable because, as I said, how will you do Drup control? In one side, your power is changing frequency, and the other side, your power is changing voltage level. Sorry, DL power is changing your voltage level. So conventional control, Drup control is also not possible. And due to this, these challenges, you develop power management strategies or schemes. So we'll discuss two strategies, and there are more that sir discussed. These were we'll discuss about it, and then I'll give it to you as a sort of home assignment because we are uh, behind our schedule. So in grid connected mode, there can be two power management strategies. One is a dispatched power mode, and the other is undispatched power mode. So in dispatched power mode, what we do is, so we can control the power exchange between the main grid and the microgrid from a higher hierarchical level. So what we do is we control power exchange between main grid and microgrid and main grid. So whenever you hear the word dispatch, that means you're controlling the active power that you are sorry, you're controlling the real power that is being taken out from that DG. So this dispatching means that you are issuing a dispatch of that source. So what you're doing is you are controlling that power exchange. If you are controlling that power exchange, what you do is there is you have to do it from a centralized agent, a centralized agent issues. So a centralized agent issues this control signal for dispatching your power to manage how your voltage and frequencies are changing. And your generations of individual AC/DC microgrid are again controlled based on two things. So output. So I told you that you are controlling the power exchange, right? For that, you have to control your DGs as well. So how do you do it? There are two ways. So one is current controlled mode, and the second is voltage controlled mode. So as the name suggests, I mean, it's quite easy to guess, right? If you have a current control mode, what will happen is your this your DG's output DG's output current is controlled to track a reference power, and when it does track its reference power, it's able to achieve a control over your power, right? And in voltage control mode, the opposite things happens, right? It's DG's output voltage is controlled to regulate its output power. So these are the two ways in which you can control your individual DGs to be able to dispatch them as and when you will require them to exchange the power between microgrid and main grid. In undispatched power, you don't control anything. So if you don't control anything, what you do is you operate at MPPT. So if you are operating at MPPT, what? So if you are operating at MPPT, how are you controlling your what you say your DGs, right? How are you controlling the inefficiencies in their output power? They can be intermittent, right? They can be variable. So for that, you use the storage to smoothen their curves so that you can have you can control the amount of power that is injecting into the system, but you are not directly controlling your DGs. So these are two ways in grid connected mode how you can control your system. Let's This is the whole complete picture. Let's discuss it first before moving ahead to standalone mode of operation. So as I said, in grid connected mode, you have two different kinds of control. One is a dispatched power output, where you control the power output from your MG by controlling your individual DGs. And in undispatched output power, you don't control anything. So what you do is, you have in them also you have two things. You have a bus voltage control mode, and in that your individual interlinking converters ILC are your interlinking converters. So these interlinking converters are between the two DC bus and AC bus. So the ILC works in bus voltage current control mode, because your bus voltage needs to be regulated, right? So ILC does that for you. And your DGs, SEs on AC bus coordinate with your DGs and SEs on your DC bus for providing dispatched power output. SEs are your storage element. In in the other mode, what it does is, to regulate the bus voltage, your DGs are used, because your DGs storage elements are used. As I said, you are not controlling; they are working at MPPT, but the storage is being used to modulate it in a way your bus voltage is regulated. And the ILC and DGs, SCs on AC bus are undispatched. They should be undispatched. And your ILC works in power control mode. So you are just controlling the power that is coming out from your DG. Sorry, I said for undispatched. So that's why. Yeah. So in one way you are working on ILC is controlling your DC voltage. I'm sorry, bus voltage. But in the other, your DGs are working to regulate your DC voltage. In undispatched, your ILC interlinking converters regulate your DC bus voltage, and your DGs work on MPPT, and your SEs are typically on charging mode, so that they are able to soften the curve of your output of your DG. Now, in standalone mode of operation, which is also called islanded mode of operation, there are two kinds of control. One is DC bus voltage control, and the other is AC bus voltage control. In DC bus voltage control, what you do is, your DGs and storage elements on DC bus are controlled using voltage control, either directly or indirectly. Directly means you are employing group control. Indirectly means you are just controlling the power balance. If your power is balancing, your voltage will balance. But in your AC side, the voltage current control is again on two types: your group control and your power balancing. And your interlinking converter on both the sides can work on three modes, either on power control mode or voltage current control mode. So this is how your standalone mode of operation behaves. So I would request you to go through Sir's lecture. I may not have done a very good job explaining this, but due to paucity of time, it is difficult for me to cover everything. So any doubts up until this point before we move on to the MCQs? Any doubts? You can give me a thumbs up or a thumbs down. Any doubts? So I'll assume that you don't have any doubts, then you will participate in this MCQ session as well. I shouldn't be the one answering all the questions. So let's talk about first question. In AC microgrid, the global control receives power references from. So anyone who has an answer, just let me know in the comment box, or they can unmute themselves as well. So if you talk about global control, it's working in direct coordination with what? A DNO or a DSO. And what is DSO giving to him? DSO wants to maintain power flow. The power flow should be in limit because it's managing a network. So what is it issuing? It's issuing a power reference for them. So the answer is what? C. So DC distribution management system, DMS, DNO, or DSO, all of them are similar एक ही नाम के वो हैं प्राणी. So this applies it to them. Second, in order to improve power sharing in group control, what kind of component is connected between the power converters and the AC bus in virtual impedance based group control? So I discussed this topic at length, so I want someone to respond. B, yes. So an inductor is added so as to improve the decrease the R by X ratio. Third, the conventional group control in a DC microgrid reduces the reference DC voltage. Uh, just a second. The conventional group control in a DC microgrid reduces the reference DC bus voltage lead to. This question is very wrong. So it's saying conventional group control in a DC reduces the reference. Okay, yes, yes. Lead to what? So how do we write the equation? We write it something like this, minus RV I naught. So can anyone answer this question for me now? So if the VDC is reduced, how is it reduced? Due to what?
Sir, increase in output current.
Yes. So if we increase the output current, if this is increased, this reference will decrease. Sorry, this reference is this. This reference will decrease. So if this happens, it's due to the increase in the output current. Fourth question, the interlinking converter in hybrid AC-DC microgrid during grid connected mode operates in what? So if we talk about this in grid connected mode of operation, okay. So in grid connected mode of operation, the ILC works on either bus voltage regulation or power control mode, but only for the DC side of it, right? So only for DC bus voltage regulation mode, it's doing it. So as you can see, ILC only is used to maintain the DC bus voltage. Here it works in power control mode, but here it works in DC link voltage control mode. So the answer is A. Fifth, global hierarchical control is what? Who can answer this? So if there is one person giving control signals, what does it reflect for the system?
Centralized control, sir.
Yes, it represents a centralized control. Next, the ultra capacitor connected to DC microgrid along with the battery is a dash device. Yes, it is a high power density and a low energy density device. It can supply a large amount of power, but it doesn't have a huge storage. So poor voltage regulation in group control DC microgrids is due to. So I talked about. So if voltage regulation is poor, that means voltage deviation is no one can tell me. So what is voltage regulation? So V at some X percent of load minus at no load divided by X. This is your voltage regulation. It is poor if this quantity is more. So if this is more, that means the deviation is high. If the deviation is high, it's only due to large group quantities. Any doubt? Next question. Which of the following entity is clear? Yeah. Which of the following entity is responsible to maintain the DC bus voltage in a grid connected DC microgrid? Yeah. Hmm. Who can tell me? A. Yes. So the converter connecting your DC bus to your utility. Just a second. Where did my single microgrid go? Here. So your this converter, this grid side converter called as GSC, it is used uh, to control the the voltage of your what was I even discussing? I forgot. Yeah. So this is used to maintain the DC voltage by working in tandem with how your utility grid conditions are. So if your utility grid conditions permit, so this DC extracts power in such a way your DC bus voltage is regulated. So that's the job of your voltage source converter connected at your DC bus. Last, the battery connected to a DC microgrid is a DAS device. This I guess we all know. See, so is it a high power density device? Can it supply power very quickly? But it depends on C rate. I mean, still it's not very fast than an ultra capacitor, that's for sure. So you can't you can't give me mixed signals, right? So it is a low power density device. We have discussed this at length in fourth week as well. You can go back to that where I discussed how the storage systems are. There I talked about how this power density curve and energy density curve varies. Yes. Next, in the hybrid energy storage system, which of the following device help to compensate for high frequency switching transients? So ultra capacitor and supercapacitor are same things, right? So don't get confused. I already gave the answer. So the answer is B, right? Can you give me any signal? Yes. Next, DC microgrids operating with adaptive resistive droop control fails to do what? No. I just told you how adaptive resistive control can affect change in your can adapt to that line impedance drop. Yes, C is the correct answer. Can provide that line impedance drop so that your circulating currents are minimized. That's what we discussed here, right? Let me open. So this group control could be used to change how your impedance looks so that your output current could be varied in a way that your circulating currents are minimized. That's the work of your adaptive resistive group control. But in it it can do one more thing. Yeah. So it can ensure proper sharing among different sources because that's the responsibility of group control. It can minimize the circulating currents. So the third option is maintain SOC balancing among energy storage system. It can't do that. How can it maintain SOC balance? SOC is dependent on how much power you are extracting from it. A droop control doesn't work in tandem with your energy storage system. It's just the output is being taken based on how much your DC voltage is being regulated, right? So to control your DC bus voltage, you are taking power from that system, but it's not maintaining SOC balance at all. So the answer is C. So it does not it fails to maintain SOC balancing. Ninth, an islanded hybrid AC-DC microgrid has excess renewable energy and fully charged energy storage systems, feeding uncontrollable loads both in AC and DC buses. Okay. The possible solution to maintain the system stability is okay. This is a very interesting question. Let's see who can answer this. So you have excess of renewable energy, you have a fully charged energy storage system, but you are feeding an uncontrollable load. So your loads cannot be controlled. And there are loads in both AC and DC buses. So to maintain system stability, load shedding is not required. Load shedding is done when your generation is less. So if your generation is there, why would you do it, right? Second, operating renewables in power dispatch mode. You can do it, right? If you control the dispatch of your renewables, you will be able to to match the uncertainty with your loads as well. So B can be a correct option. And since you have batteries, you can always rely on them to buffer your difference between how much you're generating and then uncontrollable loads. Charging energy storage systems doesn't make sense. They are already fully charged. So the correct answer is B. So Dot, did you understand? I mean, can I get your name? I don't know your name. Dot sounds very funny. Dharni. Okay. So, uh, yeah, great. No, it's not last. Which of the following statement is true in grid-connected operation of the AC microgrid? Okay, if a grid-connected operation of AC microgrid is there. So, battery charging PV at MPPT, diesel generator regulating the voltage and frequency. Battery charging PV at off MPPT, diesel generator regulating the voltage and frequency. Battery charging PV at MPPT, diesel generator turned off, and battery discharging PV at off MPPT and diesel energy generator regulating the voltage and frequency. So, who can answer this question? Can a diesel generator be used to regulate the voltage and frequency? So let's say you are at a grid connected operation, right? You have you are an AC microgrid and you are connected to the grid. So any differences, you what you have to do is you can get it from the grid, right? So what you can do is you can maintain your renewable energy sources at full MPPT and charge your battery simultaneously so that whatever the differences is covered from your battery energy storage systems and by interchanging power from your utility. Your diesel generator won't. Yes, DG will be used only when you have to power loads which are needed at all costs and you can't get energy anymore from your storage. Yes, we give first preference to other storage. Yes, that's what I was coming. So that's how you will be able to do it, right? So the correct answer is C. Diesel generator will only work when you have a very criticality or very emergency use of a load. Next, what do you mean by 5% group in local hierarchical control? So 5% means this delta F by delta P is equals to 5. Oh, sorry, 5%, right? So 5 by 100. So what does this mean? I have made it easier for you, right? So it means that delta F, if deviated by 5%, will produce 100% deviation in your power. Yes. So the correct answer is, oh, there are 50% deviation in nominal frequency causes 1,000. Okay. So 1 and 3 are correct answers. Yeah, great. Next, which one of the type of advanced group control technique? Can anyone tell me which one is the type of an advanced group control? So what is an advanced group control? We change how impedance looks. Yeah. So the answer is virtual resistance based group control. It can be impedance for AC and resistance for DC. Which one of the following statements is correct? A hybrid energy storage system combines the battery with its energy management system and ultracapacitors. Two, the ultracapacitor is a low energy and high power energy density device. So second is correct, right? Maybe D. This one, this was for the previous, right? Or this one? This can't be D, right? None can't be the answer. So because second statement is correct. So the first statement says a hybrid storage system combines a battery with its energy management system and ultracapacitors. This is also correct. So you have two different kinds of energy storage systems. One is a battery and the other is your ultra capacitors, and ultra capacitors are used to manage your fast switching transients. So the answer is both. Next question: which of the following microgrid has a DC bus as its main bus? I mean, this is very easy, right? So in AC/DC microgrid, you don't have a main bus. You have both the buses, AC and DC. Just remember that. So a main bus is only with the DC microgrid or an AC microgrid. Yes. So DC bus is for DC microgrid. Which of the following are the operating mode or S of a grid? This is very easy, right? This should be microgrid. So we can have both grid connected and islanded. What are the future research areas of hybrid microgrid? Okay. So these hybrid microgrids, so we require communication between DC bus and AC bus because both of them need to communicate. Yeah, all of them. Because both of them need to communicate to so as to be able to check how much power is required from the utility. Power management, yes. We need to check how much we need to manage power from all the resources. AC, we have DC, we don't have a global variable. We can't control all of them using just one single quantity. So this is also economic concerns too, because we have multiple sources, multiple, so the whole expenditure increases. So the answer is all of the above. 7. What are the control variables in a microgrid? It's D, right? P, Q, V, and F. All are control variables. Next, which of the following is a type of intelligent control technique? Who can tell me? All of them. Virtual impedance is not intelligent. Angle droop control is something that is, we just use a well-known formula to treat the inefficiencies of the existing droop control methods. So the answer is multi-agent based controllers. Here we have a multi-agent system. So I discussed at length. So which have many agents working to achieve a common objective, and that is generally to maintain the power deficit or sufficiency from all of the resources. 8 is done. Ninth, last question. Dash is a type of decentralized microgrid control. Yeah, yeah. DC bus signaling. I didn't discuss DC bus signaling. I guess, yeah, I discussed. Okay. So in DC bus signaling, I didn't discuss, right? Okay. So in DC bus signaling, what you do is you inject a sinusoid. So in this, no, that you do is power line signaling method. In DC bus signaling, you disturb the bus in such a way you check through sensors what is the output of all the different hardwares connected to it, and from that you control that hardwares based on whatever the offered information is available to you, and based on this you control your individual operators differently so that all of them can be used to maintain the voltage level at the main DC bus. So that is used for DC bus signaling. So that is the correct answer. Okay, so any doubts for this lecture before I bring it to a close? Okay, thank you. Awesome session. So any doubts? Dharani, we had late joinees as well. X by RS grid strength ratio. No, 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 no. The grid strength is something that is it's your short circuit ratio. That's a different thing. We'll discuss next session. We Yeah, it's a short circuit ratio. It's a different thing. Yeah, yeah, it's a different thing. So it tells you if your grid is weak to different disturbances or not. So that is a short circuit ratio. That's not something that, yeah. So anything else? I thought same as R by X ratio. Yes. No, it's different. Yeah, I hope you got the gist of it. I derived something as well. It was a long time I derived this whole equation. Yeah. Okay, so let's bring this session to a close. Thank you. Yeah, no worries. Thank you all for joining. Yeah, welcome. Thank you all who joined late. I hope that you watch this lecture on YouTube whenever it's available. Good day. Have a good night. Yeah, welcome. Okay, I will request all of you to please leave.